Okay, guys, so it's 7 o'clock, so I would suggest we start. I see we have 15 people watching. It's much less than 140 who have RSVP'd, but nevertheless, I think we should start now, such that people who are here don't wait too much. So thank you very much to everybody for joining. This is the first time we are doing such an event online, and we are still we don't have much experience with this Zoom and YouTube online streaming stuff, but we do our best that it works. Hopefully everything is working fine, video and audio. If not, please post it in the YouTube channel or on this online questions site. Johannes, my colleague, who is a co-organizer, is in the background checking the questions on YouTube and on online questions. Okay, so I'm very happy that Stephan from Databricks agreed to give 2 talks tonight. So these are 2 very interesting topics, and actually we've mentioned one of them in the past at one of our previous meetups in 2019. I'm talking about Delta Lake. I gave a brief introduction back then, but in the meantime I have forgotten everything about it, so I'm very happy that Stephan is here to give us a refresher or much more details into this topic. And the second topic of tonight is MLFlow. I'm myself very keen to learn more about it because I don't know anything about that one. Then I would say, without further ado, I'm switching off to Stephan. So I will stop my screen sharing, such that Stephan, you can stop the video. Stop the video. Stop share here. So Stephan, you can start sharing your screen now.
All right, then, great. Let's do it. All right, so thanks a lot, Bogdan, and thanks for giving myself, or in general, Databricks the opportunity to give the 2 talks today. So I must say, unfortunately, we do it as an online event because I just told it to Bogdan that I've never been to Vienna, and I was always looking forward to visit Vienna once. And so I always thought, okay, we have this meetup scheduled, and that's my chance to come there. But yeah, we have to reschedule it a couple of times. And now I think it doesn't make sense to, again, reschedule it to some later point in time, given the current situation. So, but like I said, so we're still happy to give the talks today, even when it's virtual. So who's talking today? So it's myself. My name is Stephan Werntz. So you can see, obviously, that the picture is pretty old. I think I did it as a student around about 10 years ago. And at this point in time, so I spent lots, or at least a large amount of my student budget to get this kind of picture. I made it for all these, for applying to apply for internships and jobs later on. And unfortunately, or fortunately, I didn't have the chance afterwards to get a new picture, to make a new picture. But anyway, so I'm a solutions architect here at Databricks. So what does this mean? Basically, we help customers to realize data-driven use cases on Databricks, and of course, then also to finally drive value out of their data by realizing the use cases. I joined Databricks last year in November, so around about 10 months ago. And I'm based here in the Munich office, so that's also our only office here in the Central and Eastern European region, so where we're covering Austria, Switzerland, and all over Eastern Europe. Myself, I'm living in Stuttgart, so that's also where I'm at the moment, in my beloved flat. And yeah, so what are we talking about today? So Bogdan already introduced it a little bit. So it's about data. data lakes or Delta Lake, more general. And the second talk will be about machine learning and MLFlow. In the beginning, I would like to give a short introduction about Databricks, so who we are, what are our products, how do we position ourselves in the market. And afterwards, we will directly go into the talks. So the talks are always structured as follows. So in the beginning, I've prepared some slides to give some context, some background, and explain the motivation. And afterwards, there will be a hands-on session, but don't worry, so it's just hands-on for myself, so you can just relax and consume it. With hands-on, I mean that we show how the things work in practice, basically. Okay, I think that's all. Let's don't waste more time. So what is Databricks? In general, usually when I talk to my former colleagues, or also friends, so I studied statistics, and lots of my study friends, they work somewhere in the data domain. When I tell them that I'm working for Databricks, they're always saying, Databricks, it's the Spark company out of San Francisco. And yes, this is partly true. So I think, so our founders were the guys who basically wrote the first lines of code in Spark, and I think around about 70 or 75% of the Spark code is still developed or has been developed by colleagues who either used to work for Databricks or still work for Databricks. But in the meantime, so our platform and our company, it has evolved, and we consider ourselves, or also position ourselves as a unified data analytics platform. Basically a platform where you can do anything from building up reliable data lakes with Delta, what we'll also cover in the talk later, processing any amount of data with Spark, and also building machine learning models, deploying them, taking care of the full machine learning lifecycle by using MLFlow. So we have around about 6,000 customers, over 450 partners in the region. So I think we're a pretty widely accepted platform if you want to do anything with your data. And so how does it look when we go a little bit more into detail? So we are a cloud native platform, so meaning that you cannot install Databricks somewhere on premise. And we are, at least at the moment, available on AWS and on Azure, so we can use their infrastructure. So because we do not have own compute or storage, so we just use it from the cloud providers. And from them, so we get this, let's say, this scalable, cost-efficient, and managed service for hosting all this kind of infrastructure. Then if we go one layer up, so what do we provide? We provide our so-called unified data service. So this is basically Delta Lake for storing your data in a reliable and scalable fashion. And of course, also Spark to process the data. If we go one level higher, so we have a so-called data science workspace. So this is basically an environment where all people who are working with data, from data engineers over data scientists, over ML engineers to data analysts, have one unified place to work in our collaborative notebooks. So what do I mean with collaborative notebooks? It's a notebook where you can, for example, mutually work together in one notebook. We provide you with all state-of-the-art machine learning frameworks. Here are just 3 listed: PyTorch, Scikit-learn, and TensorFlow. But we have also out-of-the-box integrated also Scikit-learn, XGBoost, and so also H2O. So whatever you want to do with data science, I think you can do it in Databricks. We also have integrations for BI tools and databases via JDBC, ODBC, but also native integrations, for example, for Power BI, Locker, and so on. Then, if we look a little bit, so how do we integrate into the cloud environments? And if we now start on the Azure side, so in Azure, we are not just Databricks, but we are Azure Databricks, so-called first-party service from Microsoft. And this brings a couple of benefits. So, for example, we can leverage all the security functionalities which are already available on Azure, all things like user management, Active Directory, You can set up Databricks by basically, it's just one click, and also the billing can be done through the Azure portal. When we think of what kind of data sources can we consume in Databricks, then it's basically everything or all services which either store data, like ADLS, blob storage, Cosmos DB, Azure SQL Data Warehouse, or which provide data, like Event Hub or Kafka. On the other side, so if we go at the, let's say, at the end of the journey or the data pipeline, so what can be the consuming systems? This, of course, can be all systems which are the source data systems, but additionally, so we can also, like I said, connect to Power BI or also deploy our models on Azure Machine Learning. Then if we go to AWS, it's basically the same. So here, again, we can also leverage the security features on AWS, user management, access rights, and also the billing can take place over the marketplace from AWS. And for the data sources, it's the counterpart basically from Azure. So we have S3 as our natural and also scalable file storage, but we can also consume data from Kinesis or from Redshift. And in the end, play out our results to either, again, S3 or deploy our model on AWS SageMaker. So I think this was the really short introduction to Databricks, but I don't want to spend more time on this and would like to focus more on the actual topics of the two talks today. And so the first one, like Bogdan already said, so it's about how to build up a reliable data lake with Delta. And so I first want to give some kind of introduction or motivation, so why we have developed Delta, then explain how Delta will solve these challenges, and then finally also show how this works in practice on our platform. So what are the typical challenges with a data lake? And I personally, so I used to work in retail before that, and we had a Hadoop on-premise environment, and I know lots of these challenges by firsthand, so just by myself. And we start on the top. So you have some, usually data lakes, they are there just to, so you need a place where you can basically, or the in general idea is just a place where you can basically just dump any kind of data. You just dump it there. Some of the data you need it immediately because you want to realize a use case, but some other data sources, you just store it there that because maybe in some time in the future, you will again need it. But often it's the case. So for example, everybody who's worked in data knows that usually these integration jobs, or in general, jobs which process data are just in theory fault tolerant. But often it's the case, or not often, but it can be the case that some of your jobs fail. So, and this is also one of my personal experience. So if your job fails in the middle of an ingest in your existing table, what will be the case? It will just leave partly, so it will leave some kind of corrupted data. And what do I mean with that? It will just, when it breaks down in half of the job, then it will just ingest half of the data. So what you need to do, you need to go to your table, clean it up, rerun the job. And it's just, so it's introducing some kind of manual efforts for this. Then the second point is, so we don't have real quality enforcement. And so also to give you some context on that, so when I think back, so we had some data, for example, some payload data from fridges. And so there was no real use case for that. So we just ingested it. And a couple of months later, so somebody came and said, hey guys, you just collected these, I think it was temperature data from the fridges. I said, yes, of course, sure. And then if you look into data, so there was some change in the schema of the JSON files. And in the end, so what turned it out? So the data was completely messed up, basically. So and what can you do now? Of course, so either you have to delete everything which is not consistent, and then if it's possible, re-ingest it again, or the second option is that you somehow have to try to fix your table. But everything, it's really unpleasant. It's error prone. And so it's not the thing. So if you're working in data, it's not the thing you want to take care of. So you want to build data products, maybe data products with some intelligence, some machine learning included, but you do not want to take care of all these, let's say, these corner cases when something fails, cleaning up the stuff and so on. The third thing is that you do not have proper transactions. So meaning that you do not always have some kind of consistent view on your data. So you cannot just, from a couple of sources, ingest data into a table and then at the same time read it all the time. So read it and get a consistent view of it. You cannot unify batch and streaming. So in general, I don't know, so everybody who's coming from this classical data warehouse world, the Dataverse world, knows, okay, so they usually have ACID transactions. And this is maybe nothing new for you, but in a big data context, it is something which was not present before. So, and how does this now impact? So these 3 points.
Stephan, can I interrupt you for a moment?
Yes, sure.
So what is your exact definition of a data lake? On the previous slide, are you referring to data dumped as JSON onto some storage like S3 or this, or are you referring to something else?
In Databricks, what we consider as a data lake, we do not have own storage. So we propose to our customer that they build up the data lake either on S3, if it's an AWS customer, so in a file system, or in a blob storage on Azure. And then,
so my question is, what do you understand by a classical data lake? Is this an object storage somewhere, or can it be also, can like SQL databases be also part of the data lake?
No. It's an object storage.
Object storage, okay.
So just think of S3 on AWS or blob storage on the other side.
Okay. Okay, thanks.
You're welcome. So now you just have these 3 points in mind. So how does this impact the building of a data lake? And if you now think a little bit about the evolution or some kind of reference architecture for a data lake, so you have some kind of events, they come in, so you stream them in with Kafka. And then, so on one side, so you maybe want to get some kind of streaming analytics. What do I mean with that? Streaming analytics in the sense that you want immediate insights into what's happening at the moment. But on the other side, so maybe you would like to do, some stuff on historical data. For example, making some reports, building a machine learning model, where you need to, of course, also derive features based out of historical attributes. And if we now want to, let's say, tackle this with the existing or with the, let's say, with the evolvement or how a data lake has been defined in the last years. So with Spark, we have native connectors to Kafka. So it's pretty easy to connect to Kafka topics. You can process it and you can really get direct insights into your data. So, but now just suppose you want, I don't know, your manager says, okay, I would also like to know which kind of products sold well during COVID times and which kind of products didn't sell well during these times. So for that, you need some kind of, or you want to do historical queries on your data. And so I think for this kind of architecture, what you see here, it's called Lambda architecture. So on the top, you have this speed layer where you just really get direct insights into the data. And on the other side, on the bottom, you have the so-called batch layer. So, and if I want to realize use cases like this, so on one side, I want to get some direct immediate insights. On the other side, I also want to be able to build machine learning models, so to build features for that and to do reporting on this. Can you do this? Yes, you can, of course. So from the Kafka topic, so you have 2 Spark jobs. One just processes the streaming data and gives these immediate insights. The other one just processes also the streaming data and stores it or persists it, writes it to your data lake. Then of course, so like we just showed, so you need to take care that your data is valid, that there are no changes. So, and that in general it's not corrupted or inconsistent. So for that, you would maybe need to impose some kind of validation, or you need to integrate some validation process into this. And can this be done? Yes, of course. So with Spark, again, we have rich RPs. We can check if the schema is the same, did it change? But again, we have to do this for both directions. So for the batch and for the speed layer. But now, so maybe your validation, I don't know. So it just realized too late that there was some corrupted data incoming. So for the streaming analytics, okay, so this is not so critical. But for your batch layer, so what you need to do, you need to again somehow reprocess this. And maybe you've stored your data and you've partitioned it, for example, by date. Then you can, of course, you can delete the partition of the last day, reprocess it, and yeah, do everything what you want. But again, this is something which is where lots of manual efforts are included. And then if we come to the last bit, so maybe there was some change in the business logic. I don't know, so you want to now calculate all products with the, at least in Germany, we have a reduced VAT from 19 to 16%. Maybe you would like to calculate the turnover based on the new VAT, and you have to do an update. So you have to update all the old records. Or you have a GDPR request from a customer who wants to get deleted. So you have to delete them out of your data. So how can you do this? And yes, it's also possible. I also can just speak from my previous experience. If we had a delete request from a customer, so we had to build a temporary table out of the full one, but without the record we wanted to delete, then we had to delete the old original table and copy back the temporary table. And you can see, so there are two things to consider. So the first one is, it's once you have to delete your table and recreate it, so you will have some kind of downtime. If you have a reporting which is running by hundreds or thousands of business users, you cannot do that. So you have to somehow schedule it because you have a downtime at the table. And on the other side, it's also a pretty error-prone process where you also have the risk that you just maybe lose all of your data. And that's why these are basically the challenges why here at Databricks, so we have also built Delta or Delta Lake as one of the, it's another one SD format, which we propose to build up a data lake, which is in the end reliable, and there are also some unperformant. So, and how do we do this? So maybe now if you're here, okay, there's Delta, it's a new data format. I just migrated everything. So all my databases, I put them, all the data in my data lake. I took Parquet as the format. And now there comes this guy from Databricks and says, hey, okay, Parquet, it's not up to date anymore. So you have to go to Delta. But you will see this is not the case, because Delta, in the end, will still store all your data as Parquet files, but we enhance or optimize the Parquet with a so-called transaction log. And this transaction log, it's just adding one additional folder to your Parquet files, where we, on one side, so as the name suggests, track every transaction. So we track every change at your table. And once there's a change, so you get a new entry in your transaction log. And what could be a change? For example, you insert some new data. You make a delete statement. You will delete some records. You do an update. All these are changes which are in the end tracked in this transaction log. And this transaction log, so like I said, it brings a couple of benefits. So first of all, we have ACID transactions. So meaning that you can have, for example, you can have multiple writers on one table and still read the table and get a consistent view of it. Then if you think back of these, one of my jobs, of my ingest jobs failed. So we have atomicity here, so meaning that data is either fully written or it's not written at all. So we do not have to clean up half of the transaction, so half of the data, and then ingest it again. So if we see our job has failed, all right, no problem, we can just start it because no data has been appended to our table. Then in this transaction log, we also store metadata about our table. So just think of what columns are included and what's the type of the column. And with that, we have so-called schema enforcement. So again, meaning that if there comes new payload, for example, if you think back of the example with the fridges, where there's some additional field, Delta will not ingest it. So it will break it. But you can also say that you would like to have some kind of schema evolution, so that it then depends. But the default value is that it will enforce the schema of the existing table. Then we can unify batch and streaming, so meaning a table can be streaming source and streaming sink. You can query your data in a batch mode, your table in a batch fashion. You can query so in a scheduled fashion. You can also set a streaming job on it. And another feature is to use these transactions. So because we know all the changes on the data, we have a feature, it's called time travel, where you can basically recover the data as it was of a specific timestamp. And this can also be used if you want to do a rollback, for example, if you maybe did something wrong. But in the end, so the main goal was to build high quality and reliable data so that you do not have to focus on this data cleansing and taking care that the data is correct, but that you can just focus on building great and cool data products with your data. So, and now how does this look, or how does this more, let's say, look in practice? So how it looks in practice, we'll see it in a minute. So how do we consider now the architecture you would need to set up for a Delta lake instead of a data lake? And I think what you can already see is there's no batch layer and there's no streaming layer, speed layer. So you just focus on building data flows. So building out business logic within your tables, because like I said, so Delta can be, Delta table can be streaming source, streaming sink, and also as sink and source for a scheduled process. And so what we always propose to our customer is some kind of, if they build data pipelines, some kind of refinement between the individual layers. And if we now look a little bit on the left, so here we have all the data sources or where data comes from. So Kafka, Kinesis, maybe some semi-structured JSON files, or just some Apache Spark data frame. And from there on, so we ingest it and process it through these different layers and realize all use cases in the end on, let's say, in one data flow. So like you see, we have streaming analytics and AI reporting, so these historical queries. So everything can be done on the same tables, and we do not have to do this separation. So how do we consider, or what do we say, how should you build up these layers? So the first one is the bronze layer. And I think also the name already suggests it a little bit. So bronze, silver, and gold, it's some kind of improvement from step to step. And the bronze layer, it's some kind of the dumping ground for raw data. So you just put everything here, just dump everything here, but you dump everything here in Delta tables. So you persist also in the bronze layer, everything in Delta tables. Then this could be something also like it's written here, so with long retention periods. And it's basically just the raw data. Then if we go one step further, so to the silver layer, so this, it's then, so there maybe you already have done some cleaning, maybe removing missing values, imputing them, possibly if you want to use them for some ML topics, or also do some kind of enrichment, for example, joining product groups with your sales data, or joining some metadata for customers, so like age and gender to your transactions. But in the end, so it's already data which can be somehow, which is consumable, but it's not this, let's say, these final tables, which in the end should be some kind of immutable and used also for this, for the realization of the use cases, which is the gold layer. So we also call it business level aggregates, project tables. And if you think of that, so this could be, for example, your features for machine learning, or it could be already some pre-aggregated data for reporting. And this is, so like it's written here, it's clean data and it's ready for consumption. So, and if we now think of the last bit of the problems. So this, if you want to do some kind of modification of your table. So like I said, it's in these standard data or big data formats like Parquet or ORC, there's no option to do an update. There's no option to do a delete. Yes, you can delete individual partitions, but if you want to delete individual records, just think of this GDPR use case where you have to remove a customer. So you probably will not partition your data by your customer, but by something like that. So this is also something which you can do in Delta. And all these features I just explained, and we will show how they work so that you also get not just the theoretical background, but that you see how this really hands-on is done on Databricks by using Delta as the format. And I would like to jump into the demo session directly. So, before we start, I would like to give 1 minute introduction to Databricks. So, if you want to know more about it, so how you can spin up clusters and how in general you can work with the platform, then please feel free to reach out. I would like to keep it to a minimum. And so this is the landing page. It's a web app. What Databricks is basically a web app. So that's the place where you pop up or where you land once you're logging in. We have some shortcuts. You see the latest projects, also some stuff to the latest releases around our runtime. I will explain it in a minute, and with respect to Spark. And then usually the first thing you have to do is to build up a cluster. And what you can see, so I've already created one so that we don't have to wait. But I just want to show you in a minute so how easy it is to set it up. So let's just call it Stephan Demo. So I give it a name. Then I can select a runtime. And this is something I would say which is pretty important. So in the end, we are talking here about Spark clusters. So about virtual machines which get spinned up. And on these virtual machines, so we need some kind of system which is operating there. And our runtime is exactly that. It's an image. So consisting of of course, an operation system, it's Ubuntu, all depending system libraries. Then we have Spark in the specified version. We have Scala, Python, and R installed. Scala always in the version you see here. And we have Delta. Then if we go to the ML runtime, this is basically containing the same I just explained, but additionally, we provide all the state-of-the-art machine learning frameworks like TensorFlow, PyTorch, XGBoost, scikit-learn, and so on. And there's also one for the genomics. So if you want to process genomics data, there are some already pre-installed genomics libraries included. I've never used it by myself, so don't ask me questions later on that, please. Then we also have a GPU runtime if you want to leverage GPU instances. Let's just select one. We have some auto-scaling options, so meaning that our cluster manager will add new worker nodes or remove worker nodes depending on the limits you set here, and depending on the workload, of course. And there's also auto-termination. So here we are on AWS. So basically you can see you can select all kinds of instances which are available in the specified region. You can also select a different one for your driver than for the worker nodes. But usually here, you can just keep it like that. In the end, if you want it to have a fast, your cluster spinned up pretty fast, then you just have to add a name, select the runtime, then you're good to go. Okay, there are also lots of other customization options. I don't want to go too much into detail, but use the already created cluster and show the functionalities of Delta Lake, and give some more hands-on context to what I've explained before that. So first of all, there's shortcuts to run it. So I don't want to do some kind of, all my colleagues told me, do a pre-executed notebook, but I don't know. I think, so I've tested it, everything worked quite well. And so I think we can just go through everything and execute the cells by ourselves. So first of all, we need to get some data. I will explain it later what exactly the data is. It will also be the same data set we use for the second part, for the ML part. But here, just for the delta demonstration. Then, so we've downloaded it. It's a CSV file, basically. Then we read it in with Spark, an API to read CSV files. We set some paths that we also have a consistent way to store our data. And then we read it in as Parquet files. Now you might ask, okay, so why do you want to read it in as a Parquet if you talk about Delta all the time? So this is just for demonstration and also to demonstrate the limitations and the benefits of Delta on the other side. So we have it now in our data frame. So in Databricks, we have these, let's say, proprietary built-in display function, which gives you some nicely rendered HTML tables, or also, if you want to, we can also make some plots here. But just so that you see a little bit, so it's some product data. We have an ID, we have a name of the product, we have the department, so product category basically, in the description. Just simple open source dummy data. So then let's do a count on the departments so that we see for all departments, okay, so how many distinct products are included here. And just for convenience, we filter out all departments which have less than 30 products included. So here you can see it's coming out. How many do we have? Sorry. So around about 58. So the next step, we will create, so now we are, just to remind you, so we want to create a delta table now out of the Parquet table, because at the moment it's stored in Parquet. And here we have this DB utils. This is some kind of, yeah, nicely wrapped shell functionality. So this DB utils, FS stands for file system, RM for remove. It's basically the same if you would type RM minus RF and then the path. So it's just cleaning up the directory. Then we can again have a look at our data, but we just saw it, so I think we can just skip it. And then we want to create a delta table out of our Parquet table. And how do we do this? So we want to create a managed delta table. That's something worth to mention. So we just say, okay, create table, use delta, specify the path, and just do a select star from our product department we have on the top. So now, as we have the delta table, let's have a look how this is structured. I haven't created it. That's why it's complaining. File not found. So it's always a problem if you do it live. Now we have it. You see, if I type %fs, then so I can write shell commands on the file system. Because there was the question before, the file system here, it's S3 in this context. And now what do we see here? So we see all these Parquet files, lots of them. And here on the top, we see this delta log. So this is the only difference between Parquet and delta when it comes to how the data is stored on the file system. And this also means that you can easily convert Parquet tables into delta tables. So it's just one-liner, convert to delta, and then provide the name of your Parquet table, and then it will add this transaction log. We can also have a look some metadata of the table. So what's the format? There's an ID. Where is it stored? You see it's here in DBFS. DBFS, it's mounted S3 bucket. We also call it root bucket on our side. You see when has it been created, modified, how many Parquet files do we have? We didn't partition for anything, so it's empty. but just some metadata. So now, if you want to have a look at how does this transaction log look like, and I could also, wait, give me 1 second. I could also show you how exactly it looks in here. If we go here inside, and then you see there are these JSON files, okay? In these JSON files, this is basically the transaction log. And what's inside here? So first of all, we have some kind of, so what have we changed at the data? So which Parquet files have we added? And here you see, okay, we have this add column, we see timestamp, we see the path of the Parquet file. So if you remember, we had 45 files. So this will probably repeat 45 times. Then additionally, we store some, we have a size, of course. We also store some statistics. So what are statistics? It's min and max values of the individual columns. So now you might ask, okay, why do you store min and max values? So what's the reason for this? So, but now if you think of, if you want to apply a filter on a table and a filter on a numerical value, and you already know what's the min and what's the max. For example, you have a column which is age, and you want to filter out anybody who is less than 18 years old. Then if you already know that in Parquet file XYZ, the minimum age is 23, you do not have to touch this Parquet file. So you can just ignore it because you already know there won't be anybody included which is less than 18 years old. And this is brings additional performance to data. But I think so all these performance topics, it could be another talk. Maybe if we do it again, then in person in Vienna. So what else is here? So we have a commit info. Don't know where here we find some kind of records. Here at the top. Sorry. So again, there we see some kind of metadata. So which cluster has it created? What was the operation? So it's now a create table as select. If I would have done some ingest into the table, I would see here insert into. If I would have done an update, I would see update. Yeah, but it's just basically adding some metadata. You also see what's the user has created, myself, here's my email address, and so on. So then if we go to the third column, so this is metadata. And this is, if you think back of the schema enforcement, so here we see, okay, what kinds of column are included and what's the type of the column. So this helps us later if we want to ingest data. And if this does not match the schema, that data will identify that there's some corrupt or inconsistent data coming. And here in the end, this protocol, it's just additional information. But I hope this is clear. So this is all the information we store next to your Parquet files. And once you do some modification on the table, there will be a new JSON file created which just tracks the changes. So then, now we would like to take this table, which is at the moment a static table, but we would like to treat it as a streaming source. So in Spark, it's nice API, we can just say instead of Spark read, we say Spark read stream, format, delta, specify the path, and then we put a local view on top of it, or a temporary view. So this view, it's just existing in my notebook. It's not even existing on the cluster, so meaning that if I would spin up a next new notebook, attach the new notebook to this same cluster, I wouldn't be able to query it. So, but you can also create global views, for example. But it's just for convenience that we can later also just execute standard SQL commands. And one thing maybe to mention about the notebooks is that you can also, at the moment, I have a Python notebook here. This is some kind of the default programming language, but you can also mix the languages in between. I just type %SQL. I can now write SQL code. I type %Scala. I can write Scala code. I type %R. I can write R code. And for Python, it's always default because I've set it the notebook is default and Python is default. So then let's start the stream. And you see now, this is a query which is running on top of a streaming table. So let's just wait till it's initializing. Drink something. So what do we see here? We have also some mini dashboards where we see how many records are processed, processing rate, batch duration, stuff like that. And on the bottom, we see the data actually. So here now we don't have a table for this. It's a chart, also an HTML chart where you have some mouse over effect and also just that you can get some, let's say, short insights. It's not a reporting tool. It's basically just for explorative analysis. So now we would like to ingest some data into our table, which we read in here as a stream. So again, it's just insert into. We have the department or product category, farm and animals. So I think these are just toys. And we want to ingest the value of 300 for this video right there. And so you can see it's processing it. And here is our farm and records. And what you see, it's increasing always by 300. So what we ingest. So it's increasing in real time. That's what also, if you think back of this speed layer. So this is this kind of real-time analytics. Of course, for a dummy example, but so it's this, of course, can and is done by our customers also with some productive and production data. So now we've ingested everything. So we have here 1,832, all good. Great. Then let's again query our table. And what do we see here? We have the same result. So now you might think this is, so what's so surprising? If I would have done the same with a Parquet file, I wouldn't have captured the changes. Then, if we go further, so just think back again of this. So I want to do some kind of update on my table. I want to delete some records. So how can this be done in a big data context on a data lake? And for that, so we again first read our data in as Parquet file. So we persist our data as Parquet file. Again, read it in as Parquet. So you see here, I just take my delta table, write my delta table as Parquet, read it in a Spark data frame, put a local view on top of it, and then do a select statement. Okay, so now we have always added this kind of record, so which just basically just artificial. So maybe now this was just, was just some dummy example, and I would like to clean it up. So, and if I want to do this on Parquet, and you see this is the Parquet table, you will get an error. So it's not possible in Parquet. You can only delete full partitions. I cannot just delete records. Then if I do the same thing, and here, look, this is on my data table, so it's deleting it. And if we now go back again, so where do we have it? So this figures, this farm and animals, so it shouldn't be present. Just trust me. Then the next case. So maybe we want to do an update. And here again, so we would like to set, this is another category, art sand, whatever is inside. So we would like to set here the count value to 2,700. Again, if I do it on Parquet, it will not work. Parquet is not able to do updates. If I do the same thing on my delta table, then query it, then check it out because it's such a high number. You see here we have the category and the count is set to 2,700. So now this is one of my most loved functionalities. It's the support of upserts or merges. And I think I said it a little bit in the beginning. So before I worked for retail, I worked in a consultancy here in Stuttgart, and we were focusing on doing data science projects in the context of marketing or CRM in general. And for most of these, so to build models for all of this customer data, you will first build tons of features of your customers. So some also call it customer 360. So some kind of holistic view of your customer, where in the end, one customer is one record with all the describing attributes. But now, so because you always want it up to date, then so every night you have some kind of job which brings in the new transactions. And there are actually three cases what can happen. So the first one is your customer, there wasn't any change, he didn't do anything, so all good. I want to keep his record or his customer profile or customer 360 view, however you want to call it, as it was, because there was no change. Okay, all right, great. Then the next thing is, so maybe he did something. He did a transaction, and now you have maybe some attributes like how many turnover has my customer done in the last year, how many products did he buy. So you want to update this profile. So what you need to do, of course, so you need to update it. And the third case is it's a new customer, so he wasn't present in the table. So for him, you need to insert him. And as you see, these are three operations. So, and if you now think if you cannot do an merge or upsert, so what would you need to do? You basically either recreate table all the time, or you apply some more complex logic, just filtering out the guys. Basically, so what we did, we basically recreated the table all the time. But if you can do these upserts, then it's actually pretty easy. So now let's create some dummy data to go for the upsert. So what do we have? We have this art sand, was 2,700 previously. We now want it to set it to 10. Farm and animals. So this is something we deleted. So it's not present anymore. And these brain teasers we want to set to now. So this is the table we want to update. And this is our table we want to like to merge into it. And on Delta, it's actually just one command. So I just say, okay, merge into my existing product table. So as it is at the moment, then I specify my merge table. I define the keys. So here it's department. And then I just say, okay, when my condition matches, so when I find the department, these guys here in my existing table, then just insert everything and then update the records. If not, just insert everything. And this, so all these transformations I just explained here at the top, all these can be done just by one simple statement. And here you see it in SQL, but we also have an API for this in Scala and in Python, where you can also build in some more complex matching rules and insert rules and update rules, of course. So let's check it out. So just to remember, if we maybe just sort, we have this art sand, it's set to 10. We have the null here for these brain teasers, and we have 2,500 for funds. Okay. So then schema evolution or schema enforcement. So keeping the data reliable, even if there is some insert of some data which does not match the schema as it was before. And for that, again, we take everything as it was. And we leave our count here as an integer, but now we add an additional column. Just something like turnover, for example. Turnover for all of the departments. And of course now, so compared to the previous table, we have one additional column. So what's happening now if I want to insert the data into my Delta table? It's not working. So Delta is refusing this transaction. And why? Because the schema doesn't match. So what, maybe you say, okay, I don't know, I'm a data scientist. I don't care about this. I just want this field here and now. So can you do this? Yes, you can do it, but you have to specify this merge schema equals true option, and then you disable the schema enforcement. And if we now look at our delta table, so you see we have this turnover column now. Okay, so you force delta to add the data, even the schema doesn't match. But maybe now, I don't know, so your manager comes or some other person comes and say, hey, you cannot do this here. So you cannot just add some arbitrary columns just because you need it, build your own table and do it there. So we need to revert it. And how can you now revert it? And for that, we have this time travel. So first thing, let's check out what we have done. What are the changes at our table? And if you think back of these transaction log, this JSON structure, so for all these entries, we add a new JSON file. And now, if we go back, so when we had a look at our transaction log, we were just here. We had just this create table as select. Then we did these 6 inserts into our streaming table. Then we demonstrated delete, update, and merge. And in the end, we wrote this additional column with schema evolution. So if I now want to roll back my table as it was, for example, of version 9, so what can I do? And this is also, it's pretty easy. I can just say, okay, select star from my table as of version 9, but I could also, I cannot just take the versions, but I can also apply the filter on the timestamp. And you see now it's the table as it was in version 9. So it has been rolled back basically. Then, so we're almost done. So let's have a look at it. So we see we have lots of Parquet files here. And usually if you ingest data in a stream, so this will create lots of small Parquet files, which in the end have non-optimal performance or are some kind of performance bottlenecks. Because you have to read all these small files. So and there's some kind of optimal size, and this is around about 128 megabytes per Parquet file. And what you can do to do this optimization, you can run a so-called compaction job. So what does it mean? I take a couple of Parquet files, I combine them by myself, and then write it out back again. But it's something you have to program or code by yourself. It's no out-of-the-box functionality. In Delta, we have a so-called optimize command. And what this optimize is doing, it's actually doing exactly this. So it will compact the small Parquet files into the optimal size. And so what you see here, I've added 1 file, but I've removed 55 files. So now you might think, okay, you've removed these 55 files. They are actually not physically removed. And why that? So in the end, when Delta does some transformation at the table, also if you do a delete on your table, it will not physically delete the Parquet file where you wanted to delete the record, but it will just recreate the one Parquet file where the record is included, but without the record. So the old data is still there. That's also why you have the ability to do this time travel. So if we now want to clean up everything. So now we have, like you saw, we have taken all these 55 files and we've compacted them into just one Parquet file because the data is pretty small. So how can we do this? For that, there's again a command, it's called vacuum. And for this vacuum, you can specify a retention period. So all data, for example, the default is around about 30 days. And all data which is older can then be removed, but you can also force it to set it to 0 hours so that you just have the current state. But then, of course, so this time travel feature is disabled. And if we now look at how is your data looking, so what do we see? We just see the transaction log and we see this one big Parquet file. And that's also the end, just a short wrap up. So what you saw, so we have all these data reliability features. So asset transaction, you can multiple writes and still query your data in a consistent way. and we have schema enforcement, we have this time travel feature, and we have all these performance improvements. So performance improvements with respect to this data skipping, what I showed in the beginning, by having the statistics about your columns in the transaction log. And additionally, we also have this, let's say, this file structure optimization included out of the box. And all these features together, this is the reason why we propose, and also for all of our customers, that if they want to build a data lake, they should use Delta as the format. And to be honest, I'm here now for 10 months. I think all customers, because we're usually talking to new customers, they are all using Delta as their standard format and single source of truth to build up the data lake. And that's it with part 1. I'm not sure how we should do it with questions, Bogdan. So
yes, let's ask some questions now, please. So hang on. So the most popular question in our online poll is: will the slides be made available on the Meetup platform after the talk?
Sorry, can you say it again? I didn't.
So if you can provide the slides afterwards, such that we can share them on the Meetup platform.
I think it shouldn't be a problem. So I need to validate it, but I think it shouldn't be a problem.
Yes, and I have a second question on top of this. Would it be also possible to get the Python notebook?
Yeah. I think the same goes for the notebook. I think it shouldn't be a problem, yes. But I also need to check it. But I think so. Here I will have a definite answer at least by tomorrow.
Okay. So as far as I know, you should be able to export it as HTML, right? Maybe you can.
No, I can export it as DBC. DBC, these are our Databricks notebooks. But so I can also export the stuff in other formats. So just if you have a look, DBC, this is Databricks notebooks, source files, this is a Python file, or you can also export notebooks.
HTML. So I think that's HTML would be the best, if you're allowed to share.
Okay, no, that's
perfect. And then let's see. So there are no more questions here on this online questions site. But I have another question. So, so first of all, many thanks for this great first part of the talk. I think it was really good. And for most of the time, I was trying to understand what is the unique selling point, or what are the benefits of Delta Lake if you compare it to other cloud data warehouses that are available nowadays, like BigQuery and Snowflake or Redshift. And so I was just trying to understand for the most part of the talk. And at some point when you were talking about the streaming, that you can read in the Delta Lake table as a streaming table. So this was actually one thing that, as far as I know, is really different from the other cloud data warehouses, because as far as I know, for instance, in BigQuery, you can't stream the tables unless you set up, I don't know. So I don't know how you do it, but it's probably not out of the box. So this was one USP that I was able to recognize. Would you agree with that, or?
Yes, it's one of the USPs. So it's really a good point, and we also have lots of these discussions with our customers. So, and in the end, it somehow turns out it's a little bit this battle between the data warehouse and the data lake. But so what are the USPs for this? So one thing you already got, it's streaming. So in the data warehouse, it's maybe somehow possible, but it's not the same thing as here if you can leverage Spark for all the streaming pipelines. And the other thing is machine learning. So we have, if you are working on a data lake, so you can directly build and deploy machine learning models on your data in a data lake. If you just think of, if you have a data warehouse, you can just use SQL. So, but you cannot build machine learning models with SQL. And what we also propose to our customer, it's not data lake, so it's called this Delta Lake, or we have a new word for it, it's called Lakehouse. so which tries to bring the benefits of the data lake, so where you can basically store any kinds of data in a very cost-efficient way, because it's just an object storage. You can process the data with any kind of latencies, so streaming and of course some kind of scheduled jobs. And you can also build machine learning models, deploy machine learning models on top of it. And so this is why this this house comes from Lakehouse. And our vision is that you also do all kinds of BI workloads directly on the data lake. So for example, we have a native integrator for Power BI, where you can directly connect Power BI to your Delta tables and do basically anything you want to do or you would like to do with the data warehouse, but on your data lake or Delta lake. And in the end, if you have a data warehouse, so what you need to do, if you just named it Snowflake or Redshift or whatever, so you need to copy your data. So you need to make an additional copy of your data to the data warehouse. So then you have the data in the data lake, and you have a copy of your data in the data warehouse, usually a copy just of the structured data, but you do not have one single source of truth for all kinds of files, formats, and sizes. Does it answer the question?
Yes, it answers it, but I don't get the last sentence because, so in Delta Lake, as far as I understood from your presentation, you also transform the original Parquet files into, the structured Parquet files in Delta Lake, right?
Yes. As you saw, so Delta is it's storing everything still in Parquet, but we add this transaction log to it. So this folder, which has metadata for your tables, which has statistics about your tables, and which captures all changes at your table.
Yes, I understand, but so you just said that in Delta Lake you have one single source of truth, but as far as I understood, you would have two Parquet files, right? The one that you start with and the one that you end up with after transforming it into a Delta table.
Because so let's suppose you already have a data lake, so all your data is stored in Parquet files, and you want to migrate to Delta.
Yes.
So you do not make copies of your Parquet files now and transform them into Delta. There's just one convenient command. It's called convert to Delta, and what it's doing, it will just add this one folder, this transaction log, to your existing Parquet tables.
Okay, I see.
Here. Wait, let me just shortly go up. Where was it? No. Sorry. So if you have a Parquet table, or if you have a Parquet file, a Parquet table, then you will, now in this case, because I've cleaned it up, so you will have lots of, or a couple of Parquet files included. So Parquet, it's here. And what is Delta doing if you want to convert them into Delta tables? And if you use this command, convert to Delta, then it will just add this folder here. So, but the data will still stay in the same place as it was before.
Okay, I see. Okay, thank you very much. And I guess in the second part of the talk, we will hear more about this machine learning stuff that you were mentioning, right?
Exactly, that's the plan. How should we do it? Should we make a break or shouldn't we? So we can also continue.
So if you need a break, I suggest you take it. Otherwise, I suggest we just finish because we are quite late. So actually, I thought we have 45 minutes and 45 minutes, but maybe maybe the second talk is a bit shorter. Let's see. But just go ahead and people can just leave the stream if they have enough. So everybody who's interested will just stay, I guess.
Okay. No, cool. Then I would say let's directly go further. So maybe, I don't know, so after the next session, maybe I can get a bottle of beer to my place and then we can do some kind of Q&A.
Yes. I have a bottle of beer in the fridge as well, actually.
So that's good. Then we can. Okay. All right. So then I would say let's continue with the talk. So wait. at the bottom, I have the data. So we'll take the same data set also for the second part. I'm sorry, I just get lost with it. But I just need to insert it, and I will just take a fraction of the data and directly write it into a Delta table, and the rest I will just stream in 100 records batches, just for convenience. So, but again, I have also some slides here. Let me just go to the presenter mode. Yep. So
Stefan, can I ask you just one more thing? Can you turn up the light a little bit because your face is quite dark?
Yeah, I'm sorry. The problem is I don't have a proper light here. This is, let me, now, I'm living here since 2.5 years, but I haven't managed to get an electrician here. So I just have some kind of standing light. Maybe.
Yeah, maybe just pull it a bit closer.
So I hope it's better now, but I'm not sure. It's better now?
Actually, it's even darker, I think.
No? That's all I can do. That's.
Yeah, I think it's a bit better, yes. So when you lean forward to the screen, your face is lightened up by the screen, I guess. When you lean forward, when you lean to the screen.
Now?
Closer, closer. Come closer. Yeah, this is good.
Okay. All right, then, yeah, let's continue with the second part. So the first one was more about building data pipelines, or in general, is how to set up a data lake. And now we want to, because usually, so what drives most of the value is, of course, to bring in some intelligence into your data products by using machine learning, giving recommendations, predictions, forecasts, and all these nice and cool things I guess everybody likes here, and also myself. So, and for that, so like I said, so we have another product. It's called MLFlow. MLFlow is our product to manage. So it's not a new machine learning library. It's something which is there to manage so all the things around training and deploying models. And because we do not want to make it so easy, so we just don't want, we don't stick to, let's say, to a single model or to a single framework. With framework, I mean TensorFlow, Scikit-learn, PyTorch, or what we think, but we can also mix them up. And that's what I mean with these multi-framework pipelines. But I will give some more context later in the talk. So, first of all, so again,
Stefan, you're not sharing the screen currently.
Oh, okay, then this makes absolute sense. That, wait, why am I not sharing the screen?
Yeah, looks good.
Great, sorry. Okay, yeah, I think so. I already gave the introduction. So, I would like to again start with a problem statement. So similar to the one we had in for the first talk with Delta. And here it's a tweet. So, and what does it say? Okay, so the story of enterprise machine learning. It took me 3 weeks to develop a model, and it's been 11 months, and it's still not deployed. And yes, so training a machine learning model. This, yeah, today this can be done so easily. I don't know. So I think lots of you guys are already involved in some Kaggle competitions. Then you have so much sample code, you have so much sample data. So I wouldn't say that you need 3 weeks if you want some kind of baseline model. So maybe you can also do it just in 1 day, couple of hours. But of course, so it's nice to build a model, but in the end, what brings the value is if you can incorporate it into real business processes and influence business decisions. And for that, you have to deploy it and put it into proper pipelines. And this is somehow also, this transition from building just a model to deploying it, and with all the things around, so this full, let's say, model management procedures around training machine learning models, that's what we want to tackle with MLFlow. So, and why is that? I think, so lots of you have already seen this, this diagram or picture. To be honest, when my former boss showed it to me, and I don't know, also the last times, I usually hate it because it's somehow, yeah, it's, yeah, I don't know what to say, but I usually didn't like the picture, but there's lots of truth included. So, and if you now just think back of what I said about, so this training machine learning models, and now you see here in this mini black box, there's the actual ML code. But around your final machine learning code, where the logic is included, so you have lots of other things to do till your machine learning code can, in the end, also bring value to your company, for your customers. And what is that? So, of course, you have to first collect some data. You have to build proper features. You also have to set up proper pipelines, which give you consistent features and within the SLAs you have for your model. So, for example, if you want to do some kind of recommendation system, so this is usually something which you should not, so you cannot send out the recommendations just every night. So this is something where you need immediate response. So where you need to display them immediately to the customer after he's logging in, after he's purchased something. Then you need a data verification. So does my model get in inference the same data as it's expecting? So the same data as it has used for training your models. Then, of course, you also need some kind of serving infrastructure. So where do you deploy a model? And some monitoring, so maybe to detect some drift, are there some changes in the data generating process before, and all these things around it. So these are, let's say, not the fancy part, but it's unfortunately the most important part. So, and now how do we on Databricks deal with it, or how do we in general position our platform as an end-to-end, now for this case, data science and machine learning platform? So if you think back in the beginning when we showed these architectures, so there were data sources on one side, then in the middle we had Delta, Spark, and MLFlow, and on the other side we had the consuming systems. And this is a little bit more if we double click on that. So how does it look in detail? So on one side, of course, we still, we need some data. So we need to store it first. For that, we can use Delta Lake to have a consistent and reliable data source. We need to prepare the data, so to build features which correlate also with our business or target variable, target outcome. Then we need a place where we can train the models, where we can also, because we usually do not just train one model, we train a couple of them, compare it, see, okay, what's working. Maybe we use different approaches, maybe some tree-based models, maybe some simple regressions, maybe some more complex deep learning models. But for that, we need some kind of environment where we can do this. For that, we have this ML runtime I just showed briefly in the cluster setup. So where all these machine learning libraries are already included. And then, of course, we need a place also how we can score our model, so how you can apply inference on it. And this could be then, again, depending on the requirements, this could be just a batch job running every night. It could be a Spark streaming job. Or you can also surface your model with an HTTP endpoint, for example, as a container. So, but all these things here, especially if you just think of the process of training machine learning models, storing them, comparing them, storing them consistently, and deploying them. All of this, for that, is MLFlow. And now I would like to go into the details, so why this is the case and what exactly is included in MLFlow. So in MLFlow, it basically has 4 components or pillars, and I just want to give some brief introduction or briefly explain what's included. So the first one is projects. In projects, it's some kind of convention for organizing and describing your model, or let's say in general, your code, which in the end yielded to your machine learning model. And doing this in a consistent way so that your colleague, for example, 2 months later, can just easily reproduce it, or some automated tool can also just reproduce it. Just think of it, it's some kind of convention. And also, for example, if you train a model and if you want to persist it, so sure, if you have a scikit-learn model, you can just pickle it, but this is not a full picture. And in this project, so it's also included that, for example, if you have a conda.yaml file stored next to your model, it does not think, okay, this is just some random text file, but it knows, okay, this is the conda environment I've used to train my model. Then if we go further, so MLflow models. So this is also, it's a general format and also kind of convention how you store your model and describing, so what are the components included and also what is the flavor of your model. With these flavors, I will talk about this a little bit later, but important thing is also these flavors. So these are flavors, means these are things which can be understood by all kinds of deployment tools. So what is a deployment tool? Just think of Amazon SageMaker, AWS SageMaker. So, and for example, if it's a scikit-learn flavor, then you need, so then the tool recognizes, okay, it's a scikit-learn model, I can, and then apply it. Then the third component, it's tracking. So if you want to build a new machine learning model, so usually you do not just do one run with some fixed parameters and then you're good. So you compare maybe different framework, different models, like I said, regressions, some tree-based stuff. Then you often also have lots of hyperparameters. If we think of these tree-based models, like in a random forest, how many trees do I want? How do I cut my trees? How deep are my trees? If I have a deep learning model, so what's my batch size? What's my dropout rate? And all these artificial large set of features you can think of. So, and all these features, as the name suggests, they get tracked by MLflow. Additionally, we can also track metrics. So what are metrics? For example, a loss for a given run, F1 score, accuracy, whatever you like to. And so you can also add some kind of tags to your model so that which you can later query. For example, this is a model for use case. So a tag could be use case equals, I don't know, demand forecasting. And last but not least, so I know lots of things, it's also tracking the models, and it's tracking the models in exactly these formats here. So by leveraging these standardized formats which come from MLflow and which in the end can also be used to deploy it not just on Databricks, but also on other deployment tools like SageMaker or Azure ML. And the fourth part, it's the model registry. So what does this mean? It's something, it's something like a model store where you can, in the end, once you're satisfied, you have your model, you can share it with your colleagues. And you can also hand it over to some other guys who, for example, to the data engineers who finally deploy it. And it's a central place where everybody has access to it, but you can also restrict the access. And additionally, you can also add so-called lifecycle. You can do lifecycle management. So what does it mean? You can set your model into staging, into production, or into archived. And this does not really put your model into production, but it's adding some metadata to it, which you can later use to, for example, to replace an outdated model. We will see this, I think, and it will be way more clear once we have done the demo session. But just for you now, so the basic theoretical concepts behind it, so what's included. So if you now want to train a model, and here we come again with these flavors I just mentioned in the beginning. So a flavor could be TensorFlow, it could be PyTorch, XGBoost, Keras, scikit-learn, Spark, MLE, Onyx, H2O, or if you want to mix a couple of them together, So, and this is, then you can also build your own custom model or custom flavor out of it. And that's what we will do later in the demo session. But in the end, so you train your model. So of course, you have to decide beforehand, so what kind of flavor you want to use in the end. But then, okay, so you train it, you have 2 models. Then, if we come to the tracking part. So like I just said, so tracking means you can just basically track everything, metadata, parameters, metrics, also artifacts. For example, if you want some kind of feature importance plot or confusion metrics as HTML, you can just easily also track this, even if you don't need it for deployment, of course, but just for documentation. Then we have this model registry. So once then you're fine, you've trained your model with the framework you want to use or with your custom framework. You have tracked it. Now you want to share it among your colleagues with the model registry. And so here you register it, and then you have these different stages. And these stages, they can be greatly used, for example, for handing over. Just think of, you have one model which is running in production. So it has at the moment the stage production, and now you detected some kind of drift in the data and you want to retrain it. So what are you doing? You're retraining your model. In the end, you again register it, and then you put your model into production, which automatically will remove the old one from production. So this means in the end, if you want for your inference code, so for your scoring job, you do not need to make any changes like this, because you just say, give me the latest model which has the status in production. And then, so you do not have to make any changes here. It's just registering it, setting the metadata, changing the metadata from staging to production, and then you're good to go. And then on the other side, so the data engineers, deployment engineers, whatever, they can then put the old model into archive. But so the important thing is, so this handover between data scientists to train models and other involved persons like data engineers, ML engineers to deploy it finally. So it's really smooth. And especially it's smooth if you want to replace an outdated version of your model. And then later on, of course, so you need to, for the serving part, so what can you do? And this is again because of this very generalized format. So you can just score your model with some kind of inline code, just apply scikit-learn to some data set. You can containerize your model. So we have functionality in MLFlow to directly build from your stored or tracked model to build a container out of it, Docker container, which you can then ship to, for example, to Azure Kubernetes Service or the counterpart in AWS. You can integrate your model into a Spark job, Spark Streaming, Spark Batch, or of course, you can also use all the other inference services which are provided by the cloud vendors. And that's the theory. I would now like to go back again to the demo session.
So Stephan, maybe a short question from myself. So is MLFlow a tool or a service that can be used completely separated from Spark or Databricks, or is it deeply integrated such that you must use it in this sort of ecosystem?
It's an open source project, so same as for Spark, same as for Delta, but in Databricks, of course, it's very natively integrated. But you can use MLFlow also for models where no Spark is involved. So, and you can also use it in your on-prem environment.
You don't have to set up Spark or something else to use the MLFlow stuff.
No.
Okay, thanks.
We'll see also, we will, so later or here in the demo, we will not use Spark for training the model. So, but I will show later how you can still use your, let's say, we always call it single node machine learning. So if you use scikit-learn, PyTorch, or TensorFlow, all these frameworks, they are usually just working on the driver node, on one node. But I will show how you can then maybe train your model in this fashion, but deploy it in a distributed way by using Spark. But this is no obligation, so you can just use it.
Okay, thanks.
So, all right, I think the intro to these 4 components of MLFlow, I think we're good to go. I hope my data is ingested. Yes, it's still writing some chunks. That's great. So we basically do the same thing. So we create a delta table. We also build up a new database just for convenience. Then take this as the standard database, and now check out how our table looks like and how our data in general looks like we want to later use for the machine learning part. So, and what's the use case here? So we have these text descriptions, and what we would like to do is to make a prediction of the department based on the descriptions. And of course, so usually for all these ML algorithms, so we need to transform the data that we have some numerical values and not just text. So this is what we'll do in a second. Then we can, again, I would say just skip it so we can, or let's just run it. So we can also, again, describe the history of our table. Just remember, we have created it pretty here in the end of the last hands-on demo. And here you see all these batch ingests, which are running here. Okay, it's now finished. You see, these are 99 chunks of around about 100 records. And that's also why we should have here 100 versions of the table. And so one of them was just to create, and the other one were these append operations where you just inserted some new data. So here again, the use case, so taking the description, this can also be done with the image, but maybe if you wanna test it out, and then predict the category. So is it some kind of, I don't know. It's usually these are toys here. Is it some science fiction stuff, some jewelry making, some card games, all these things. So let's just get a basic idea of how our data looks like or how it's distributed among our departments. You see, so the most occurring category is vehicles, then we have science fiction, fantasy, Disney toys, packs and sets, dice games, and so on. All right, so this is the same. Then from these delta tables, we can also get the version of it. So you see, this is something which is here. So we just query it and take the top one or the max out of it. So why do we do this in an ML framework? So if I want to have the full picture of how I've developed my model, I do not just need what kind of framework did I use, what kind of hyperparameters did I use, but I would also need what version of my data did I use, because the data, so it's not static, it's evolving, there's some new records coming. And this is something, for example, I can just extract it, and I can also track it later next to my training run, so that I know, okay, I have a random forest, there were 50 trees included, and I trained it on my delta table version 100, just to get the full picture of it. Then, and I think that's just what you meant, Bogdan, so we will now leave the world of Spark completely. So we will put everything into a pandas data frame so basically in the memory of the driver, and use this for training our models. So then next step, we have lots of imports. So all the scikit-learn functionalities, also from MLFlow, the scikit-learn module, MLFlow, pandas, all these things. Then, so we need to prepare the data, of course. So first we need to encode the labels. So because at the moment it's text. Then we split the data into train and test by taking around about 1/3 of the data for validation, and the rest goes into the training. So now it's prepared, and then let's use a simple scikit-learn pipeline. And what do we have in here? So we just say, okay, I want to build 75 decision trees in the end and average them. Then to transfer this text into numerical features, so in scikit-learn there's a count vectorizer, which basically counts the occurrence of a word in a record, but always with respect to the full set. So it's just basically just giving you out integers, and you can also set how many features, because if you just unionize all these descriptions here, you have lots of different words, and in the end, so I would, because my data set is also not so big, so I would probably have more features than I have records. So you can parameterize this, and then in the end of the pipeline, so this just, like I said, so this just transforming the text into some numerical values. The second part here is then applying a random forest model. Pretty simple. Have I already? Yeah, already executed. So how does it now go with MLFlow if I want to track my model? And you see it already here. So there are some kind of built-in functionalities. So first I have to tell that I want to track my model with MLFlow. But the good news is, so if you have some already existing code for training on machine learning models, there's no change needed at the actual logic of your code, but you need to wrap it inside this functionality here. And for everybody who has worked with scikit-learn, I think this should look here, everything pretty familiar, but I just initialize it here with this MLFlow start run, and now MLFlow knows, okay, now I have a new experiment, a new training run. Then I get my pipeline, I fit my pipeline to the training data, I get my predictions on the test data, and then I calculate an F1 score as a metric. Pretty easy. Then in the end, I just say MLFlow, okay, log my parameters, so number of trees, number of estimated, set some text that I can later identify, log my version of the data, so this is delta version we did in the beginning, and log as metric and the F1 score. And then in the end, it's just one line of code, MLFlow log model. And you see here, and this is what, and it's in the beginning with these flavors, I say MLFlow.scikit-learn, and this means now I have a model with scikit-learn flavor. So what's happening? You see here at the top, there we have this experiments button. And now you see, I tested the notebook. So before we started the talk, so that's why there are so many experiments here. But if you just look at the timestamp, that's from now, okay? So what we see here, we see our two parameters we tracked. It's the delta version, number of trees, and our metric. But that's not all. Let's just hit it here. So there's also an UI with MLFlow, where we have a link to the source code. So what notebook did we use? Was it successfully finished? How long does it take? Parameters, metrics, tags. And now here comes the most important part. It's the model part. So how is it stored? And if you think back, so about these MLFlow models, so this component of it, it's exactly that. So on one side, it's some text file additionally, which describes, so a YAML file, which describes, okay, so what is what? So environment, it's my Conda environment. It's contained here in this Conda YAML file. What's my loader module? This is the flavor, basically. It's a scikit-learn. Then what kind of Python version did I use? What, how did I pickle my, my model? It's a serialization format, what scikit-learn version I use. Then here I see my Conda environment. So to get the full picture, also to reproduce it later, and also to deploy it somewhere else without having all these imports beforehand and taking care that the version is the right one, that I do not use scikit-learn 0.1 something. And I have my model here as pickle file. Okay, great. So I could now, and if I go here, you see this is this register model, and that's this model registry, but I will not do it now because the talk is about custom models or multi-framework models. And hopefully we will also get some better predictions if we combine it a little bit and have something more advanced here. So, and what's what's the motivation? So why should you, let's say, mix it up? For example, I would like to use the pre-processing from scikit-learn, and in the end, I don't want to use just a simple random forest, but I would like to build some deep learning model by using Keras. And that's exactly the use case here. So in the beginning, we do the pre-processing, so basically transforming the text with this count vectorizer into numerical features. Then we apply then we train a Keras model. And then additionally, there's one extra step, because if you just do inference with this, with the model, so you will not get so-called human readable labels. So you will only get some label between 0, so some integer values. But this is nothing you want. So we will also implement this mapping between the integers, the predicted integers, and the actual compartments. So here it's a little bit summarized. So we have first label binarizer to for our label variable, so the department, then count vectorizer to transform the text into numerical features, and then we apply Keras to train our model. And in the end, because we do not have now, let's say, as above, this predefined scikit-learn flavor, so we will use the most general one, and this is just a Python function. So basically everything which can be done in Python. So you can also save your scikit-learn model as Python, as Python model, or as Python flavor. Okay, so enough of talking. Here, it's not so you have to add some additional code here, because you're, because of these, let's say, more advanced way of training your model. So I have a class here. So it's basically just my my class, which on one side does all the encoding steps. It's doing this tokenization of the features, and it's also training. So my my Keras model here. You see here, so it's really, it's nothing sophisticated. I didn't tune a lot, so just a couple of dense layer, and always after dense dropout layer. And then in the end, so I apply a softmax function to get also the final labels out. Okay, then here, and if we have this kind of custom model, we need to build our own customized log model functionality, or at least say how we can store and persist the stuff. So, and what does it mean? So you see here, we have this tokenizer, so this count vectorizer. We have the encoder, so transforming the labels to the classes. Then we have, and then we have our Keras model. In the end, these are all artifacts. So in MLFlow, like I said, you can also store arbitrary artifacts. Then what else do? We extract the current conda environment, and we add the dependencies for the libraries we've used. Here it's hard-coded, but you can also do it programmatically. And then finally, here we have the same functionality as above with this log model, but here we do it in this PyFunc flavor, where we can basically customize everything we want to do. And what do we need to do that here? We have to set a path, so just how is it named? Then we need to add the final scoring of inference code. This comes in a second, so that you will get some more context on this. We add our conda environments and add all the artifacts. And artifacts, like I said, so it's here we have the encoder saved as JSON file. We have the tokenizer pickled, and we have also the model pickled. The model is stored as H5. Sorry. So how does our custom model now look? And this is a convention you need to do. So in the end, you see it's extending this Python model class out of MLFlow. And we need two methods here included. And the first one is load context. So load context basically loads all the things we just persisted at the top. So label encoder, tokenizer, and the model. That's what's done here. So this is the first thing which gets run, and which in the end loads your model into the executors. And we need a predict function. So, but this, you can also see it if you go to our documentation. So there's a little bit, yeah, mini example. So here it's a little bit more extended, but just to be aware. So in this class, it also gets serialized. You see it here, that's our Python model. And here you can really, be as creative as you want. So you do not have to stick to any kind of framework or any kind of pre-processing or afterwards processing. It's up to you. So you can code anything. Then, so now we want to train our custom model. So this multi-framework model, so where we pre-process the data with scikit-learn, and in the end, build our network with Keras. And for that, so to keep in mind, at the moment we are in a single node machine learning framework. So we do just run everything on the driver, and our worker nodes, they are basically idle, and we just pay for them. So, and how can we solve this? And there is this package is called HyperOpt, and this brings two benefits. The first one is, so HyperOpt, it's not just doing this, let's say, stupid kind of grid search where you just try out thousands of parameters and then in the end select afterwards the best one. No, it's testing a couple of sets of hyperparameters, getting back the results, so your metric, your loss, your F1 score, whatever, and then based on what it learned, it will determine the next set of hyperparameters. So, and how does it learn? So it's called tree of Parson. So it's a Bayesian method in the end. That's one feature. Then when we think of these idle workers, so how can we use them now? And that's the next cool feature. So with HyperOpt, we can leverage our cluster for the full process of parameter tuning. What does it mean? So I do not just have this, let's say, optimized determination of the next set of hyperparameters, but I can also, so HyperOpt will distribute, it will take a couple of different hyperparameter sets, send it to your worker nodes, train the models on the worker nodes, calculate the metric you have, send it back to the driver node. Then from there, from the driver, it will again determine the next set of hyperparameters based on this. Take the next set of hyperparameters again, sends it back to the worker nodes till you have specified how many runs it will do. Okay, I hope this was somehow clear. So, but you will see it. So I think the story is, it's not just, so it has some intelligence involved, how you determine your hyperparameters or the next iteration of hyperparameters, and you can distribute the training process. So for that, now, because we have a more complex model, so we also have a couple of hyperparameters, so batch size and size of how many dense layers we want to add, how large are dense layers, how many epochs, max features, what's the activation function, and what kind of optimizer do I want to choose, and what's the dropout rate. Then, I don't want to go into detail of all these functions, but in the end, this here is, wait, let me just check it. Exactly, so model and score HyperOpt. So this is in the end a function you want to minimize. And this is also why I've added here, because F1, so the bigger, the better. So I've just added a minus here, and there's also some status. And this is something after each training run, so after each training run, on our case, on the worker nodes, this is what HyperOpt will send back to the driver node. So I can also add, for example, just the model here, the object of the model. Or I can also add some other arbitrary stuff. But these two things, they need to be included here. So how does it look? Let's just start. So in the end, we have this Spark trials. And the Spark trials means that it's distributing the training process to the worker nodes. Set parallelism equals 4. This means that at the same time, you're training 4 models at the same time with different hyperparameter sets. Then you need a function which you minimize, and this is this guy here, model and score hyperopt, here at the top, which in the end, so yes, it calls this one here where your model is. This one builds your model. This one applies it to your test data, and this then in the end calculates a metric. But I don't want, like I said, so we will not too much of the details here. So, and then I've specified that I would like to do 30 iterations. So it will test out 30 different sets of hyperparameters. But in a distributed fashion. So it's Spark now. Even if we just use the standard machine learning frameworks out of, from scikit-learn and from Keras. So let it run, because it had lots of things to do. And I think if we just think back, what was our best model? Where is it? Okay. Yeah, the problem is now, so it will add 30 experiments here because we do 30 runs. We can check it out. It's here. So what do we have? So we had a F1 score of 0.65. So it's almost ready. Around about 0.68. So I'm sorry when I'm overrunning here all the time. But in the end, okay, so we have now a model. It's trained. So how does it look? If we now go to the MLFlow UI, then let's just go on at the top. Now you see this nested run here. And within this nested run, so the run before, this was our individual run, our random forest. And here we have our custom model. And at the top, we have the best of these models. So this will automatically store it here. There we have lots of parameters, lots of metrics, all the things are stored. But I want to show you how is it stored in the artifacts. How are they stored? And here in this artifacts folder, this is something we did before that with this log model. So we have the classes, we have our Keras model, and we have the tokenizer. So for doing this configuration. Then the ML model, now we have a PyFunc flavor. It's what you see here. Here we have determined all the passes for the artifacts. And again, we see all which kind of versions we have used. If we go to the Conda YAML, so there we see, okay, Keras 2.24, TensorFlow 1.14, and so on. And now if we want to register the model, so how does it go? And I've already, here it's Stephan test. So this is this model registry. So you see one button, I've now registered it. And if we now go here on the left into models, just type Stephan test. So here we go. Here's our version we've just registered. So now you see the stage. This is what I said in the beginning. What can we do now with it? So we can set, okay, stage, put it into production. And like I said, it's not putting it into production, but it's adding some metadata. And this metadata we will be querying later, okay, in 1 second. So we can also have some kind of confusion matrix and stuff like that. Here, this is the code if we want to put our model, register our model with code, and also put it into this production stage. So you see there's an interface MLFlow register model. So we can first extract the best model, then register it. Then we can say, okay, transit it into production. So now we have it. So how can we now deploy or make inference on it? And for that, let me jump here just briefly. if we want to apply it now. So how can we extract it from MLFlow? And this is what I said in the beginning. So with these, okay, you do not have to make some changes at your model code. It's at your inference code. You just leave it as it is. And why that? If you look here, I just specify my model name. Then I set up the MLFlow client. And then I just say, hey, client, give me the latest version of my model name, which is in the stage of production. And then I automatically will fetch the model I've just trained and replaced. So, but if I now come 2 weeks later and train a new model, then I don't have to make any changes here. I will just pull model 13. And now if it comes, how can I apply it? So here you see here, MLFlow.pyfunc load model. Then I just load my production model. And here I have some kind of product description. And for that product description, we get the category vehicles. Second thing, I'm almost done. So if I now want to apply it, let's say in a distributed fashion. So I want to use Spark to apply my model because I have tons of data distributed. So what I can do, I put this inference code into a so-called UDF, user-defined function, which in the beginning, when it's initializing, it's loading the model in all the executors, and then it's applying the model batch-wise on my Spark data frame. And how does this look? So you see here, sorry, yeah. At first, I don't have data. No. So now I have also the data. Sorry, just I can apply it now here. And if I want to apply my model in a Spark streaming pipeline, I can just do the same. It's here, predict department, UDF, applied on description. And then I get out all these results here in batch. And here, if I now hit here, it will initialize my stream and apply my model to it. So, I'm sorry for overrunning, but just 1 minute to wrap it up a little bit. So with MLFlow, as you saw, it's very open when it comes to what kind of model you want to, let's say, train with MLFlow, persist and deploy. So all state-of-the-art machine learning libraries are out of the box included with very convenient tracking functionality, so to track the model in a consistent way, but you can also build out these custom models if you have the requirement to do some more fancy stuff on it. And as you also see, so this model registry, it's really nice and it's really a handy process to hand over models as a data scientist to your data engineers. And trust me, in these months at Databricks, I saw lots of stuff. So people training models on their local laptops, then somehow trying to derive some SQL code out of the model and then putting this into a some stored procedure where it's just applied every night, but just a SQL code. So this is by no means really convenient, not error-prone process here if you use MLFlow for this. And it's, like I said, it's open source, and you do not have to change any of your code. You can just use your existing training code as it is, but you have to wrap it into this MLFlow framework. That's it. I'm sorry for overrunning.
No problem. Thank you very much, Stephan. It was also a great second talk. So we have indeed one question from this online questions tool. The question was, if you know Neptune.ai, and if you do, how does MLFlow compare to Neptune AI?
What? I'm sorry, can you say again?
The question was if you know a tool named Neptune.ai, like the planet Neptune. And if you do, how does MLFlow compare to that? I've Googled it and it seems to be indeed similar to MLFlow. So it's a lightweight experiment management tool for machine learning experiments.
I'm sorry, I've never heard of it, so also not.
Yeah. So I guess that answers the question. You haven't heard about it, then posting the link here in the
okay, that would be interesting.
in the Zoom chat.
Curious. So what are the other tools? But MLFlow, it's not just tracking. So when I just got it right, so this it's more about tracking the things. Here, it's really not just about tracking some parameters, metrics, and maybe even a model. So it's the full lifecycle. So storing them, deploying them, and also this lifecycle management. If you have some kind of new model you want to use the old one.
I see. Thank you very much. So there are no other questions in the online questions tool because there a timeout occurred and I can't log in back to it. Let's see the YouTube channel. No other questions either. So I have another question. This web UI that you've shown, I guess this is only available in Databricks, or is this also available in the online, in the open source version?
This is a very good question. I think it's also available in the open source version. So, but you need to host it somewhere.
Yes. Okay, I see.
But I just used it in Databricks. So that's the point. But yeah, I just used it in Databricks. There are also some other cool features. For example, I can also, you see here, I can compare some training runs. There are some plots here. I can, yeah. But I think it's, I'm not sure. Don't name me down. So I think it's also available in open source version, but you have to take care of hosting all the things by yourself. Okay. Databricks is really convenient, integrated.
Okay. Well, yeah, looks great. So very interesting. Well, me personally, I don't have any other questions. So thank you very much, Stephan. I see we still have 15 viewers. Let me switch on my video. Okay, so thank you very much. It was a great pleasure. Also, thank you very much to all the listeners, the participants on YouTube. And I guess we'll stop now because it's also already quite late. And yeah. I guess I'll just go down and have an offline dinner. Yes, and looking forward to an end of this Corona time and meeting in person here in Vienna.
Yeah, me too. Like I said, I want to go to Vienna, so it's next time.
Yeah, so you are invited, officially invited, as soon as these crazy times are over. Thank you very much, Stephan. Have a nice evening.
Bye-bye.
Bye.